Hello, everyone. Thank you for joining me in this talk today as I elaborate how you can use event-driven architectural patterns to decompose monoliths to microservices using AWS services. Before I get started, let me tell you briefly about myself. I am Parnab Basak. I'm a solutions architect at Amazon Web Services, servicing our worldwide public sector vertical. In this role, I work with state and local governments and education technology companies to help provide solutions specific to the needs of their industry. I specialize in building net new solutions, as well as modernizing or re-architecting existing applications, such as they are cloud native using modern software practices like serverless, DevOps, and analytics. I do have a packed agenda today, so in which I discuss the what, how, and which of your modernization journey using event-driven architectures. To level set the context, I first briefly describe the building blocks of what a monolith, a microservice, and a serverless mean. Then I talk about a few patterns to help decouple a monolith to microservices. Lastly, I end the talk about a few considerations that you should keep in mind as you choose an appropriate AWS service for your re-architecture. I would certainly leave time for some Q&A at the end, but feel free to post your questions in the chat window as we go along. With that, let's get started. First, let's level set by defining the building blocks of our talk. With that, let me introduce you to monolith architectures, which I believe should not be something that is alien to you. A monolithic architecture is the traditional unified model of the design of a software program. A monolith in this context means composed of all in one piece. A monolithic software is designed to be self-contained, wherein the various components of the program are interconnected and interdependent. All application concerns are contained in a single big deployment. I showed multiple variations of this monolithic architectures where essentially they might be layered. In some cases, you might have an application with composed of a UI, a business logic, and a data access layer interacting with a database behind the scenes. Or sometimes you might simply have a client side, a server side interacting with the database perspective as well. They may also be composed of various layered architectures, example being the model view controller patterns, or they may be composed of submodules within it. But all in all, they're deployed as a single executable so any changes to the application requires a new version of the whole application we built and deployed. In our quest, let's next define what a microservice is. As per Martin Fowler, the microservice architectural style is an approach to developing a single application as a suite of small services, each running on its own processes and communicating with lightweight mechanisms, often as an HTTP resource APIs, or in our case, over a certain set of protocols that define event-driven architectures. These services are built around business capabilities and are independently deployable by a fully managed or automated deployment machinery. There is a bare minimum of centralized management of these services, which may be written in different programming languages and may use different data storage technologies. Microservices architecture brings the following advantages. They're independently deployable and allow for a more team autonomy. They're independently scalable. And this leads to improved maintenance because now the ownership per team is on one set of services versus the whole. Having understood the advantages of microservices, the next question is, how do you pull it off? One method that we have found extremely beneficial here at AWS is the use of a 12-factor application methodology to design microservices at scale. The 12-factor methodology is a set of 12 best practices to develop applications to run as individual services. They work well both for decomposing monolithic applications into microservices or for developing cloud-native applications from scratch. While you can read more about them in depth on the website 12factor.net, I would like to draw attention to just a few of them, which I've highlighted in black, that is of particular interest in our talks today. Dependencies. You should be declaring dependencies explicitly and isolating them as and when required. Then you should be creating a backing services for attached resources like config, etc. You should scale out via the process model and have a concurrent set of services reading from a queue or a topic, and we'll discuss what a queue and a topic is as we go along. But you should also develop them as a stateless processes on a certain business metric. You should be able to quickly dispose of, meaning you should be able to maximize the robustness with fast startups and graceful shutdowns. And then all other services would be interacting via APIs. In a nutshell, what each of these mean, or in a nutshell, what all of these mean is each microservice has its own data model and manages them independently. The data moves within microservices using dumb pipes, such as an event broker or a lightweight protocol like REST. And then each have a small scope that encompasses a single business functionality in its entirety. Then internal operations are a black box, which are only accessible by external programs via APIs. Let's also call out the different terminologies that I'm going to use in my talk today interchangeably. A message is an item of data that is sent to a specific destination. In a message-driven system, an addressable recipient awaits the arrival of messages and reacts to them. Otherwise, they lie dormant. That's what a message is. Now, you might ask, what is then an event? An event is a signal emitted by a component upon reaching a given state. In an event-driven system, notification listeners are attached to the sources of events such that they're invoked when the event is emitted. This means that an event-driven system focuses on addressable event sources, while a message-driven system concentrates on addressable recipients. A message can contain an encoded event as its payload and be used interchangeably all throughout my talk today. Lastly, in streaming, an individual message doesn't make much of a sense. You need to aggregate and perform certain operations on them to gain more insights about your application behavior. Next, let me introduce you to serverless. If you see the evolution of your responsibility matrix, virtualization gave you only the abstraction of the underlying hardware. With containerization, this evolved to you having to manage the application code, its configurations, and the updates over the base image. Lastly, with serverless, you don't have to manage that even. Serverless is a cloud-native development model that allows developers to build and run applications without having to manage servers. Serverless technologies feature automatic scaling, built-in high availability, and pay-for-use billing model to increase agility and optimize costs. These technologies also eliminate infrastructure management tasks like capacity provisioning and patching, so you can focus on writing the code that serves your customers. And all this comes with enabled security as well. If you choose AWS as your cloud service provider, we enable building modern applications as serverless first, a strategy that prioritizes the adoption of serverless services so you can increase agility throughout your application stack. We have developed serverless services for all three layers of your stack, meaning compute, data store, and as well as integration. On the compute side, look at AWS Lambda, an event-driven pay-as-you-go compute service that lets you run code without provisioning and managing servers. On the storage side, look at Amazon DynamoDB, which is a key value and document database service delivering single-digit millisecond performance at any scale. When building microservices, integration is a very common aspect. To that end, we have Amazon API Gateway, which is a fully managed service that makes it easy to create and publish APIs at any scale. We will talk other services in this layer, especially the integration layer, in our next slide. But note that these are just a few of many that include serverless data warehousing, big data processing services, etc., all built using serverless technologies. Since we're talking about event-driven architectures today, let's talk about a few AWS services that enables you to do that and falls into the integration layer we were talking about earlier. We are categorizing these services into two sections: AWS Native, services built in-house within AWS, but made available to you to help you improve faster, move faster, lower IT costs, and scale efficiently. Then there is a set of managed open source services. These services that we host for you of the open source products without you having to take care of the underlying hardware's administration. In each of the category, there are two further subcategories as well. One is called the event store, the other is the event router. So event store is where an application can persist an event and then can read from it later as an immutable source. Then there is event routers, which collects information or messages from one or more tracked applications and then filters and pushes them to appropriate consumers. There is a subcategory of queues, streams, topics, and buses, which we're going to talk about in much more depth later. But let me talk about a few services that fall into this event store and event router category. The first is Amazon Simple Queue Service, or Amazon SQS, which is a message queuing service enabling you to decouple and scale microservices, distributed systems, and serverless applications. Then I have Amazon MQ, which is a managed message broker service for Apache ActiveMQ and RabbitMQ that makes it easy to set up and operate message brokers on AWS. This has also intelligent routing built into it, and hence it works both as an event store and as well as an event router. For stream processing, which we would not discuss much in depth today, but I would like to call upon a couple of services in that category, is Amazon Kinesis, that allows you to easily collect, process, and analyze video and data streams in real time. And then there is Amazon Managed Streaming for Apache Kafka that helps you securely stream data with a fully managed, highly available Apache Kafka service. Let's next look at the event router category and a couple of services there. The first is Amazon Simple Notification Service, or Amazon SNS, which is a fully managed messaging service for both application to application and application to person communication. Lastly, there is Amazon Event Bridge, which is a serverless event bus that lets you build event-driven applications at scale across AWS and existing systems. Now, let's next get into the business of understanding how should we start about decomposing a monolith to microservices using event-driven architectures. To make it more contextual, let's first define the problem at hand and then go about how to do it. As an example, let's think that you have been tasked to decompose a monolith that comprises of a UI front-end layer, a back-end layer, and a database layer running on AWS cloud. Maybe it's running on a virtual machine in your account that you own. Assume this layered system comprising of a model view controller abstraction paradigm, but at the end of the day, it's a layered architecture nevertheless. This can be any application in any domain, but since we being Amazon, I would say there's an e-commerce website like Amazon.com or a retail store website like BigBasket.com, which runs mostly on AWS. The end users are interacting with the UI layer, viewing products, ordering products, checking their order statuses, etc. The challenge that you have is, since this being a production-grade application, you have to split the application into a set of smaller interconnected services with minimal disruption using event-driven architectures. You may ask why event-driven, and my simple answer would be reliability and scalability. By abstracting producers and consumers from each other, you achieve true decoupling. You can increase responsiveness of your clients by using asynchronous events. And lastly, your services can scale and fail independently, making them interoperable. To that end, my first pattern is called the Strangler Fig pattern. We want to incrementally refactor our applications so that we can learn from the process and change our minds if needed. A technique that has been frequently used when doing system rewrites is called the Strangler Fig application pattern. Martin Fowler first captured this pattern inspired by certain type of figs that seeds itself in upper branches of trees. The idea here is to create a new system to coexist and then grow it, potentially replacing the old system. So let's take that into action. First, from the UI front-end layer, create an intermediate proxy to be able to reroute certain requests to your new set of microservices. Services such as Elastic Load Balancers and Amazon API Gateway allows you to do path-based routing. In our example, I'm allowing all requests to go to the existing backend and then only routing certain set of requests, the requests for my new orders, to my new sets of microservices built using AWS Lambda. This AWS Lambda function can then insert the orders data to its own database following the 12-factor app methodology. And in this case, I have chosen DynamoDB as my data store. Now, if you have a requirement to sync this order data back to the legacy database, then you can use a feature of DynamoDB called DynamoDB Streams. Let me talk about what a DynamoDB Stream is. So DynamoDB Stream captures a time-ordered sequence of item-level modifications in any DynamoDB table and stores this information in a log for up to 24 hours. Essentially, it is an ordered flow of information about changes to items in a DynamoDB table. You can have another Lambda function reading from this stream and updating your existing data store in near real time. The pros for the overall pattern here is it provides a way to reduce risk when doing system transformation, because you're doing this keeping in mind the original application as well, and you're only pulling in new microservices as you need them. So keeping old systems in play while refactoring to updated versions minimizes the risk, minimizes the dependency, and minimizes the overall impact of a whole-scale refactor might bring in. And also have a look that what I'm changing here is only the UI front-end layer, while the rest of the application from the backend and onwards still remains the same. Let's talk about the next pattern. The next pattern is called the message interception pattern, wherein I'm using a messaging service to fan out the event to new and old components both at the same time. So each of these branches can use a filtering mechanism to read only selective messages that is their point of interest and then act upon them. Using this fan out pattern and using the event store as a buffer, subscribers can use a filter policy to pick out selective messages. For your existing backend, if it cannot be modified to receive messages directly from this event brokers, then you can always have an AWS Lambda-based interceptor that reads the messages from the event store and then translate them to the backend call, keeping the backend as is. Like in the previous pattern, the data can also be synced asynchronously using DynamoDB streams and AWS Lambda if you have a requirement to keep your legacy data updated as well with the order data that is now going to a different service. The pros for this pattern is both the old and the new can now receive the same set of events to read if they choose to do so and act upon them differently. The intermediate messaging layer that we have built here can also be used for all future refactoring without requiring additional changes. So tomorrow, if you have an invoicing service and a payment service, they can still read from the same layer without making any changes to the overall architecture here. The next pattern that I'm going to talk about is called a decorating collaborator pattern. While the previous two patterns asks you to make changes to the UI and the front-end layer, in some scenarios, you might not be able to do so that easily. Maybe your front-end is too complex to change. Maybe it's owned by a separate team that you have no control of. Maybe you may not have a front-end at all. In such cases, modifying the backend could be an option. In the decorating collaborator pattern, what you end up doing is you alter the backend to now post messages to an event store in an asynchronous way. Here, I'm using a SPY service, which may be an interface to push out the same set of messages to this event store. And of course, if you need the data to be synced, then the orders microservices can also pull in the data from this event store and process and store it in its own orders database. And of course, if you need the data to be synced back to the legacy database, DynamoDB streams and AWS Lambda can help there too. The advantages of this being a non-plugging event-based asynchronous messaging service, it obviates the wait time that is required for waiting for a response. And this is simple to scale as well. Makes all the future migrations for that same pattern without knowing about each other's existence. Here, the original backend service doesn't know that there has an order processing service also growing up parallelly. On the other hand, the order processing service doesn't know where was the source of this data, if it's coming from a backend or some other event sources. So the last pattern in this category is the change data capture pattern. With change data capture, rather than relying on that interceptor model to make all calls either in the front end or the back end, we can react to changes made to the data store and then push them to an event store as well. We create something called create data capture triggers on the legacy database and then publish those to a message broker. The new order service subsequently reads out of the broker and it posts it in its own database. Some databases have transaction logs too of all the database entries, and those can also be sent over to the event store. Now, since the original database is already synced by the front end and the back end as well, there is no need to do the sync again. So here I've not used this similar pattern of DynamoDB as well as Lambda to push over to the legacy database. But if there are further requirements that you need it, you can of course include it as a part of your design. The advantage of this pattern is that there are no changes required in the original application stack. The new service grows completely independently and organically as a separate new one. Now that we know how to do it, let's understand which AWS service can you use to get you there. So before we go into that detail, let's understand the basics of messaging first. Essentially, a messaging architecture comprises of a producer application A generating messages and publishing them to a medium. The medium or the channel might have built-in routing or translation capabilities before they are sent or pulled by the receiver. There are things that you have to consider or be aware of while using such an architecture. The first and foremost being, how does the producer authenticate with the channel? What protocol should it use to push the messages? Then when it comes to the messages itself, what type of messages should we use? Do I need the messages for a command, or do I need the messages to be of request reply type? Or is it of rather event type? Then what are the characteristics of the underlying channel? Is it a point-to-point based, or is it a publish-subscribe based? Then how does the channel know which recipient to send the messages to? Then, of course, there is a consideration that does the message content need to be enriched before the receiver starts consuming it? And finally, how should the recipient interact with the channel and be able to pull or be forwarded the messages automatically by the channel? So these are some of the many considerations that you should be worrying about if you are using an event-driven architecture as part of your monolithic to microservice migration. So most messaging applications can be reduced to a series of interactions that adhere to one of the following message exchange patterns or MEPs. The first being point-to-point. In the point-to-point domain, message producers are called senders and consumers are called receivers. They exchange messages by means of a destination called a queue. Senders produce a message to a queue. Receivers consume messages from the queue. What distinguishes point-to-point messaging is that a message can be consumed by only one consumer. This shows a more complex picture of a point-to-point messaging to illustrate the possibilities offered by this domain. But understand that the point-to-point domain offers a number of advantages. Messages destined for a queue are always retained, even if there are no receivers. This allows you to also do load balancing to scale message consumption if the order in which the messages are received is not important. Then the next pattern is the publish-subscribe messaging pattern. In the publish-subscribe domain, message producers are called publishers and message consumers are called subscribers. They exchange messages by means of a destination called a topic. Publishers produce a message to a topic, subscribers subscribe to a topic and consume messages from the topic. And the main advantage of this being that it allows messages to be broadcast to multiple subscribers. For both these patterns, I show a one-way communication, but note you can always extend this to two-way communication using two separate channels, both for the request and the reply queues. When evaluating an event channel technology against your business and critical requirements, keep in mind the following common characteristics. First and foremost being infrastructure. Does the underlying infrastructure need to be managed and tuned by the channel owner? Is it serverless? Is it managed by the cloud service provider? Or do I have to manage it myself? Then there is push versus pull. Are events sent to the consumers, or do the consumers need to fetch the events from the channel? Then there is ordering. Are events guaranteed to be delivered in the order that they arrive? What if I have a strict requirement to receive messages in the order that was published? Then there is latency. How soon after a publisher publishes a message will it be available to the consumer? Can you introduce a wait time in between? Maybe a delay? Then there is duplication. Can duplicate messages be introduced if the publisher is pushing in duplicate messages because of many other reasons? Will these duplicated messages in the channel be deduplicated automatically, or would the receiver have to find a mechanism to decouple it? Then there is message size. What is the maximum size of messages that can be posted? Can you alter that attribute to fit in larger ones? Then there is fan out. Can each message be delivered to or processed by multiple consumers? Then there's message retention and archival. How long will the messages be stored in the channel? What's the default? What is the maximum? Then there's filtering as well. Can even consumers choose to receive a filtered subset of the message passing through the channel? Or can the channel be very specific as to send specific set of messages to specific set of consumers. Then there is message replay. Can the message channel resend messages to new or existing clients that request them, even hours or even days after those messages was first published to the channel? Then there is failure handling. What happens when the messages that can be processed in a timely manner, either by the producer or the consumer? Maybe there's an erroneous condition within the producer or the consumer application. Maybe the producer and the consumer applicators might fail to interpret aspects of the protocol that they need to use to communicate. And lastly, there is message schema. Can I create a schema to define the structure of messages that are sent to the message channel so that everybody knows what that uniform structure looks like? So again, these are just some of the considerations that you should be worried about when designing or selecting your service to architect using EDA. But again, this list is not exhaustive, but it may serve as a useful starting point for you orienting yourself with the characteristics of the underlying channel. With that being said, if you're looking at AWS as a cloud service provider and looking at an AWS service to adopt based on these parameters, I present to you a comparison chart of all the AWS services we were talking of earlier and have these attributes laid down explicitly for them. Do note that these are not complete by any means, as there are more features within each service for you to explore. On a high level, understand that Amazon Simple Queue Service or Amazon SQS, Amazon Simple Notification Service or Amazon SNS, and Amazon EventBridge are essentially serverless, while the rest are managed services. All services except Amazon EventBridge provide you with some form of ordered messaging capabilities. Messaging services, and each of them have different maximum message size constraints, while some can retain messages for longer periods. For those that have size constraints, there are mechanisms to also bypass those and probably use a reference attribute to an original store, then be able to pull up those messages from. These services can either offer at least once or exactly once delivery guarantees. Amazon Kinesis, Amazon Managed Streaming for Apache Kafka or Amazon MSK, and Amazon EventBridge offer repay capability as well as message schemas on AWS. Except Amazon Simple Queue Service, the rest are PubSub based. And finally, all services offer both encryption at rest and in transit by default in AWS. So in summary, decompose your monolithic architectures in phases using EDA, apply the appropriate patterns based on your use cases. And we talked about 4 patterns there, or use a combination of the patterns that best suits your needs. Choose the right AWS service for the right job based on what you need to get done. And you can use multiple set of services, even within the same architecture, to get the job done. In all, what this will allow you to do is, it will allow you to achieve loose coupling, scalability, extensibility, availability, and remove dependency complexity by decomposing monoliths to microservices using EDA. I just touched the tip of the iceberg. So if you would like to know more, visit our website dedicated to everything serverless at serverlessland.com. Join the AWS developer advocates that host that event for a weekly live virtual office hour sessions. In each session, we talk about a specific topic or technology related to serverless and elaborate on it. I hope this talk helps you in your modernization and refactoring journey involving microservices and AWS. Thank you for your time and have a great rest of your day today.